Om Shri Sai Ram. Today we are going to start the chapter called Magnetic Effects of Electric Current. In the previous chapter we have studied about electric current, right? So in this chapter we will study about the magnetic effect of electric current. It is one of the effects of electric current. So first of all we need to understand how many effects of electric current are there, and then in precisely we will go and talk about magnetic effects of electric current. So let's start effects of electric current. Now if you see in this picture, animation to be precise, this is a conductor, right? The electrons are flowing in this and you can see the red dots, those are atoms. When these electrons are flowing, it is ruffling up the atom, right? When it ruffles up the atom, it creates the heat, which we call as heating effect of electricity. The practical application of heating effect of electricity is, you can see here, electric heater we use, electric room heater, electric iron, electric kettle, even to the basic instance, we can use electric bulb. The filament heats up and it produces light. So these are the practical applications of heating effect of electricity. Now let us go to the further effect. Effects of electric current. You can see here, what is here? A beaker, two electrodes, and you can see the water bubbles are going to one or the other electrode. Some bubbles are going to this electrode, which is called cathode, one is going to anode. So when the electricity is passing through this solution, what is happening here? It is the chemical composition of this electrolyte, we call it conducting solution, is getting what? A chemical reaction in it, and it is decomposing it. H2O is decomposing into H plus ions and OH minus ions, and we are getting the gas here. So this is also the effect of electric current. Yes or no? Because if you pass electricity, the chemical composition of this solution is getting changed. This is also an effect of electric current. Now let us go to, this is called as chemical effect of electric current, as we discussed. Now the final thing, the most interesting thing. Have you seen this anywhere? In olden days, now also we use it. To ring a bell, a person has to physically go there and strike the clapper to the gong which you have, and the sound produces. That is a kind of ringing a bell. Now as the technology progressed, these kind of instruments came in market and we are using in these days. What are these called? Electric bells, right? So how do it work? Nobody is physically going there and ringing the bell. So how it rings by its own? One thing is for sure, electricity, when you have electricity, then only you can ring the bell. When the power is off, you can't ring the bell, right? So there is some relation between electricity and this bell, so that's why we call it as electric bell. And we need to understand how it works. If you remember your 8th standard physics, you can recall the phenomena called as electromagnet. Do you remember that? How it works? Now, similar to this electric bell, I switched on a fan. How it rotates? So, do anybody physically going there and rotating? No, right? It rotates by itself. And similarly, any motor vehicle, how it goes? So the underlying principle of everything, this electric bell, fan, tape recorder, or any motor vehicle, is the magnetic effect of electric current, which you are going to study in this chapter. It's a beautiful phenomena, because of which there is a huge progress in the scientific field after this discovery. To study about this magnetic effect, we need to know about the magnet first. Yes or no? Then only we can know its effects and we can simulate these effects when we flow past the electric current. If you don't know about the magnetic field and magnetic effects, then how can we simulate that effect by the passage of electric current? So first of all, we need to study about the magnetic effect. As a child, I was so much curious about the seamen, right? When any explorer or people who go on expedition, they're in the middle of the ocean, how they can figure out where they have to go? There are no landmarks. There are no any traffic signals. You go this right 50 kilometers, you will get this harbor. There are no any such kind of things. How they know? This raised my curiosity. Then when I searched it, researched on this, I came to know about this wonderful instrument called compass. What this compass is? A compass is a device having a magnetic needle that indicates the direction on the Earth's surface pointing towards the North Pole. First of all, to add to my curiosity, I just kind of thought how this compass know that it has to point the direction which we call north. It always points the north direction. Now, and when you take a bar magnet near a compass, it goes haywire, it goes crazy, right? When you keep a compass on your hand and bar magnet next to it, it goes crazy, it goes in some other direction. So we got to know that this magnet is doing something to the compass, right? Now let us study about the magnets. Magnets are very mysterious objects. You attach them with one side, they'll attract. You just reverse it and they'll repel. What is happening? The same magnet is attracting on one side and it is repelling on other side, right? So by this observation we concluded that it has two poles. One is North Pole and one is South Pole, and unlike poles like north and south attract, like poles repel, north and north, south and south repel. So as we understood this, how do we imagine the influence around the magnet? Now if I take iron box or something made of a magnetic some magnetic object around the magnet, it kind of attracts, right? I'm not physically connecting it. I just put it near it. What happens? It kind of attracts. So how do we imagine the influence that the magnet is producing around it? We need to know that. So for that, let us play. How do we play? We take small iron fillings. Iron fillings are small, minute iron crushes. So what you do, you take a magnet and drop iron fillings, or you drop iron fillings and place a magnet in between. Let us see how it reacts. See, the magnet is dropping down. Oh, you can see the beautiful pattern that is coming up, right? Once again, let's watch it so keenly. As the magnetic filings are raising up, it is forming the pattern by its own. Nobody is doing it. If you want to draw it, it comes out to this structure. It is similar to it, right? It is so interesting pattern, so beautiful pattern, like somebody has drawn it. So how do we conceive it? So what is happening there around the magnet? What do you observe? The first part of the scientist, the first part of an observer, a student or anyone, to see the nature and note the key observations what we observe. So from this, what we observe? The key observations of this magnetic field, what we are seeing. Area around the magnet is influenced by the magnet. That is for sure, right? The area here, the area around the magnet is getting influenced. You can see the patterns of lines. So you can infer that this magnet is doing something around this for sure. Right? The second point, magnet influence does not spread forever or becomes very less as the distance goes farther and farther, which means this magnet, if you place the magnet here, the influence of this magnet, if you can see this part, that part, in the corners, you can see the iron filings are not that affected as it gets affected near the magnet. Near the poles, you can see how much dense the particles are. As you go away, you can see they are more or less influenced, but not that influenced as it gets influenced near the magnet. Thus, now we can say that magnet creates a magnetic field around it, which we call a field. It is influencing the space around it, that we call as a magnetic field. If you place a magnet, it has an influence around it, depends on its power, magnetic power. Now, how do we define magnetic field? That's what we discussed now, right? The space around the magnet in which other magnetic objects get influenced by it is called as magnetic field. So any object that gets influenced, any objects, to be precise, any magnetic objects that gets influenced around the field, we call it as, around the magnet, we call it as magnetic field. Now we studied about the magnetic field. If I go to previous slide once more, I can show you one thing. You can see these lines, right? Some random, not a random lines, you can some handwritten lines. It seems to be somebody has drawn it. So how do we intuitively explain these lines? Let us go and dig deeper. Magnetic field lines. See, this is an experiment we are doing now. What we are doing is, we are placing a magnet which is north pole on one side, south pole on one side. Take a compass and drag it around. And while dragging, the point to be noted is the north pole, the direction of the compass, it always points the north pole. Start with the north pole. Where it points the north pole, make a point. Here, drag the compass here. Where it points the north pole, again plot a point. Drag it here. Where it points, plot a point. So as you drag it around, you have different points and join those points. When you join those points, what happens? You will see a beautiful loop of lines. You can see beautiful loop of lines. At everywhere, what happens? You place a compass, take a compass, see the arrow. Where the arrow is directing, it always directs towards the north pole. Plot a point, drag it around the magnet, and plot all the points which you have already plotted. Connect all the points which you have already plotted. So you will get these beautiful lines. So by seeing this experiment, what we can observe? We have done the experiment. Now we need to observe. What we observed? That observation we will write as properties of magnetic field, right? Magnetic field lines forms continuous loops. Yes or no? It is forming a loop. From north it is going to south. From north it is going to south. From north it is going to south. One thought-provoking question I will ask you. When you place a magnetic compass near north pole, so north pole will be pointing away from the north pole, right? The direction of the compass will be pointing away from the north pole, outside the magnetic field. If it has to form a closed loop, if you imaginarily take the compass inside the magnet, what happens? Where the field line will be? It will be from south to north, inside the magnet. Outside the magnet, it will be north to south. Thus, it forms a closed loop. Do you understand? Now the second. Now, the one more thing. Greater the number of lines per unit area, higher the intensity, stronger the magnitude of magnetic field. This in short means you can see near the poles, you can see this area. If you plot this area, if you can see this area, this has so many lines. In the same magnitude of area, if you plot here, if you not plot here, if you just take here, the same area you take here, same area you take here, how many lines of field are in this area? How many lines of field are there in this area? You just compare them. You will get the more field lines here, you will get less field lines here. It is basic intuition, right? Because if you take any object this near to the magnet, it will attract even more when compared to when you compare with an object that has been put here, right? If you put a magnetic object here, it attracts more. That means the magnitude of attraction will be more when it is having more lines of field. See, greater the field lines per unit area, higher the intensity. Higher the intensity means the magnitude of the magnetic field is very much high. Magnetic field lines do not intersect. Why it does not intersect? Why should not intersect? You can clearly see it is not intersecting. Do any line intersecting with any other line? No, nobody. It is going by itself, coming back. It is going by itself. It is not interfering with this line, or this line is not interfering with this line. Why it is happening? Why shouldn't it cross, the lines cross with each other? By our definition, what we told, the magnetic field line is a line where if you take a compass, it should point the north pole. So we just connected all the points that is going from the north pole to south pole, right? If the two lines are intersecting, for example, what happens when two lines are intersecting? You have a common point. When you have a common point, you take your compass there and put it on that common point. So what happens? The compass cannot say this is the north, this is not, because those two lines are intersecting. One says this is the north pole, one says this is the north pole. The two intersected in the between, and if you place the compass over there, it will go haywire. So our definition allowed us to constrain this one. So no magnetic field lines will intersect. No magnetic lines will. This is the most important thing in this observation. Properties of no magnetic lines can intersect with each other. Now the basic points to note what we have studied until now about this magnetic field. Are these magnetic lines are real? No, they are not real. But it is for our understanding to make us easy to understand. It is for to make us easy to understanding very intuitively. No, the field lines are imaginary, which makes us easy to understand intuitively. Those are not real. The one more point we need to note is magnet creates magnetic field around it, and magnet's existence can be intuitively represented through magnetic field lines, which means if you have magnetic field lines, then you can say there is a magnet there. That is the summary of this. That means if you have magnetic field lines, if you have a compass and it is deflecting, you find a magnetic field line, that means you have some magnet around it. That is the meaning of this. Now let's go back. Let's go back to history, where we used to believe that there is a particular substance that is called lodestone. Right? We used to believe that lodestone, naturally occurring magnetized piece, attracts other magnetic objects. So we thought that this is only the magnetic object that can attract all the other magnetic object. Okay, these are the magnets we used to play in our childhood days, right? These are the magnets. This is naturally occurring magnets, which comes from the mineral called magnetite. So we thought these are only the magnets. On the other hand, what we thought, the flow of charges is electricity, right? So flow of charges is electricity, and magnet substance is different. Magnetism and electricity is different. as we thought before. And that thus we concluded we used to believe electricity and magnetism are two separate entities until this man came. This man came and revolutionized the whole science. Hans Christian Oersted, one of the leading scientists in the 19th century, he showed that electricity and magnetism are related phenomena. They two are not separate entities. Those are related phenomena, thus played a crucial role in understanding of electromagnetism. We have electromagnetism as a subject now. They used to not have this subject. When this man came into picture, he observed something beautiful, then this field got started. His research created technologies such as radio, television and fiber optics. Fiber optics is a thing nowadays we use to transmit the information for the long distances. So this is also based on the principle of electromagnetism. So because he invented such a huge thing, we need to honor him, right? This unit of magnetic field strength, this unit of magnetic field strength is named the Oersted in his honor. We need to honor him. So for his efforts, so what we gave? We gave the unit of magnetic field strength as his name, Oersted, right? Now so many students may be curious how he did it, right? Even I was curious how he did it. Let's go and explore it. A beautiful phenomena. What happens, see here. When during his lecture, he was explaining his students in Germany. It was around 1803 or 1802. What happened is, he was doing his experiment. He switched on the circuit and there was a magnetic compass nearby. It started deflected. Suddenly his eyes went there. Why is it deflecting? See, the switch is on, it is getting deflected. Off, and it is coming back to its normal position. That means this current is doing something to this compass. When the compass can deflect, when there is a magnetic field, then only a compass can deflect. Right? As we saw earlier. So he concluded that yes, this current carrying conductor, we know, right, conductor means which allows the current to pass through it. This current carrying conductor is producing a magnetic field around it, which is causing this compass to deflect. Do you understand now? Now he went crazy. Wow, the electric current carrying conductor is just behaving as a magnet. And we can visually see like this. If a wire is like this, current is going in this way, it is producing circular magnetic field around it. Thus, we can conclude electricity and magnetism are both sides of the same coin. It is not the different entities. They are the both sides of the same coin. If electricity is there, you can see the magnetic field around it. If there is a changing magnetic field, you can see electricity around it, electric field around it. So these two are coupled. These two are not the different entities, they are interlinked with each other. So to conclude this session, let us conclude with a beautiful note. The Oersted, as we talked about the Oersted, what he did is, when he came to Germany for his research, he was influenced by a philosopher called Friedrich Schelling, who used to believe that all phenomena are correlated in one absolute and necessary law, from which they can be all deduced. They can all be deduced. See how much spiritual thought it is. He is telling that every law is a unified law. Every force is we have all forces coming from an absolute and necessary law. This electricity, magnetism, optics, friction, mechanics, everything comes under one umbrella. Let us find that umbrella. See, when a scientist has this kind of approach, When his approach is beyond physical, then you can see the nature very keenly, and you can discover the unhidden beauty in the nature. With this note, we can conclude this session. Before going, I'll give you some questions. You can try it out and answer it to your instructors. First question is, why does the compass needle gets deflected when brought near bar magnet? So easy question, you can able to answer it, I know. Second question, a magnet is placed on a paper, but a compass constantly points one direction when it is significantly distant away from the magnet. What should be the reason? You can intuitively think, when an object is there near the magnet but significantly distant, far away, so why the compass is pointing in that direction, not changing its direction? You can intuitively think on it. The third one, the most important topic which we discussed, can two magnetic field lines intersect? Yes or no? And you need to justify your answer. Okay. With this, I hope you enjoyed this lecture. So thank you, Sairam.